In this video we are going to study how to solve second order ordinary differential equations with constant coefficients. The basis for this the text that I am going to follow is Stewart's Calculus, the 7th edition. And we have for the second order ODEs, we have two cases. We have homogeneous and non-homogeneous cases, and both of them have constant coefficients. So in case of homogeneous equation, we will have something like A, then y second derivative plus cy equals 0, where a, b, c are constants. Okay, and in this case we have the same thing on the left side, but on the right side there is some function g of x, again a, b, c constants. Okay, so let's call this one, let's call this two. Now one is easiest, but it is also the most important case, and 2 is a bit complicated, and there are just for the methods that we are going to show, for some particular cases there are easy ways to solve. Everything else is then needs more or other methods like series solutions that we are also going to present in some of other lessons here on this channel. So let us say one homogeneous case, and I will at the same beginning homogeneous, sorry. Okay. Of course, we speak about linear differential equations, so that's the topic here. Now, when we have our second order homogeneous differential equation, what we get here is also, along with it, we get the so-called auxiliary or the characteristic equation. So characteristic, I prefer to call it characteristic equation, and that equation is obtained when we, instead of y, put r, but the order of the derivative is the order of the equation. The motivation for this we are going to see later, but basically the characteristic equation is just obtained as a plus b plus c equals 0. Now we put here, since here is y prime, we put r squared, y second derivative, then y prime, here you put and so which is r to the power 0, so that we end up with ar squared plus br plus c equals 0. So this is the characteristic equation. As we know, this is in R, because a, b, and c are real numbers, and as we know, there are three cases according to the discriminant. And there is this table, so roots of AR squared plus BR plus C equals 0 and general solution. Now, as we know, R1, R2 can be real and distinct. In this case, the solution, the general solution is C1 e to the power R1x plus C2. Then we have R1 equals R2 equals R. In that case, we have that the solution is C1e plus C2x ERX. Okay, and the third case is, of course, when R1, R2 are complex and they are then conjugate. So let's say alpha plus minus I beta, and the general solution is then e to the power alpha x C1 cosine beta x plus C2 sine beta x. Okay, so this is how we are. This is the table, and this is, as you can see, what makes these types of equations so easy. So we just find out what are the roots and plug in into this form of general solution, and that's it. Again, I'm here, I like to simplify, I like to take the essence of the things, and then when you know the basis, when you know the basic things, you understand them well, you then can proceed with that. And we will later on see why is this the case. So we are not going to leave this unexplained. We will exactly see why, and why this exponential function appears here, and so on. Now let us see one example. So the first example says solve the differential equation y, the second derivative, minus y prime minus 6x equals 0. Okay, so you can pause the video and try, and here is the solution. So in this case, a equals 1, b equals minus 1, c equals minus 6. So we have the characteristic equation r squared minus r minus 6, here is plus, sorry, here is plus, so here is also 1, and here is plus, equals 0, and you can easily see that this is the same as minus 2, r plus 3 equals 0. So r1 equals 2, r2 equals minus 3. Those are the roots. And so they are real and different, so distinct. And if you look at the table, then we have the general solution is y equals c1 e to the power r1 is what, 2, plus c2, what is e to the power minus 3x. Okay, and this is the okay. Let us see. One more example. Solve differential equation 3 y second derivative plus y minus y equals 0. Okay. Now, the characteristic equation is 3r squared plus r minus 1 equals 0. And you can show that I will just use here. So, r equals minus 1 plus minus square root 13 over 6. So again we have real and distinct, therefore y equals c1 e to the power minus 1 plus square root 13 over 6x plus c2 e to the power minus 1 minus, okay, I don't need here, brackets, so minus square root 13 over 6x, and that is the general solution of this equation. Okay. Next example. Solve for y second derivative plus 12y plus 9y, so plus 12y prime plus 9y equals 0. So answer. We have the characteristic equation. So characteristic equation is 4r squared plus 12r plus 9 equals 0. And the solutions are, now this can be factored. So we have, this is the same as 2r plus 3 squared. Okay, and so r equals minus 3 over 2. And what kind of solution is this? This is double, and of course it's real. And if you go back to the table here, you can see that is this case here. So that is the general solution is y equals c1 e to the power minus 3 over 2x plus c2x e to the power minus 3 over 2x. So that is the general solution for this case. Okay, and we have one more example, and you can guess that it will cover. So this is number 4. So solve the equation. Okay, so y second derivative minus 6y prime plus 13y equals 0. Okay, so the characteristic equation is then r squared minus 6r plus 13 equals 0. And we can see that then the equation is, so the solutions are 36 minus 52 over 2 equals 6 plus minus square root 16 over 2, which is 3 plus minus 2i. And we can see that these are complex, okay? And here alpha is 3, beta is 2, because regardless whether it is, so we just take the positive. If you take R1 equals A plus I beta, or let me just be here. So R1 is 3 plus 2i, then alpha is 3, beta is 2, and we take the positive one. So for the solution we are taking the positive, and using this case now here, that is the general solution given by e to the power, I will just write here c1 cosine beta x plus c2 sine beta x. And now, so y is, what is alpha? Alpha is 3, so 3x c1 cosine 2x plus c2 sine 2x. And this is the general solution. Okay, so this is our the examples. So where I just want you to see how to solve. Basically, this is reducing the differential equations to the some skills which are from pre-calculus or high school algebra. So there is, of course, some knowledge of the complex numbers. Now, since we are in calculus and this is a higher level course, we of course want to know why this table. So why this table? So why exactly we have these solutions? So I'll just this. Okay, so if you okay, so why do we have this table? Okay, so let's see. We have the characteristic equation. Now, first of all, let us see the motivation. So the first thing is, what would be a solution of the second order homogeneous equation? Now, in words, so which function? So we need a function that, so to say, scaling its second, first, or I'll just say second and first derivative and first derivative and add it to itself gives 0. Now you can see that, well, maybe you cannot see if you are not experienced and you are not supposed to see, but if you look at the exponential function, but not the usual exponential function, and you know something about derivatives, which you know for sure if you have reached this level. Know, for example, that if you have the function e to the power rx, so the composite function, then if you start taking the derivatives, first derivative, okay, then so the first derivative is what? E to the power rx times rx prime, which is rx. Then if you start taking the second derivative, that is the derivative of the first derivative, and you will end up with something similar. So if we take or guess that y is e to the power rx for some r real number, of course different from 0, because 0 will then make it okay. It just will not make it interesting. Then if we put that into equation, we get a erx plus b e to the power rx prime plus c equals 0. And if we take this into the consideration, we get this factorization. Now this is always different from 0, so this has to be equal to 0. And this is now what? Characteristic equation or auxiliary equation of the differential equation of the second order homogeneous with constant coefficients. And now, as we know from high school algebra, from pre-calculus, there are 3 cases. The first case is when b squared minus 4ac, so which is called the discriminant, is greater than 0. So in that case, we have 2 linearly independent solutions of the equation.